Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the topic velocity in Cartesian coordinate. To better understand the topic velocity in Cartesian coordinate, it's very important for you to know what the Cartesian coordinate system is and what velocity is. From there we can move to velocity in 1, 2 and 3 dimensions. For those who didn't have the opportunity to watch the lecture video on coordinate systems, I advise you go back to the channel's video and you pick the video on coordinate systems and watch to better understand the Cartesian coordinate system. Having said that, let's now look at the term velocity. So the velocity of a body or a particle simply refers to the rate at which the displacement of that body changes with time. The SI unit of velocity is given as the meter per second. So velocity in one dimension. Generally, velocity is calculated for one-dimensional motion as a ratio of the displacement vector to the time. So mathematically, we have v vector equals r vector on t. In calculus terms, we talk about instantaneous velocity, which is calculated as the first-time derivative of the displacement vector. Mathematically, we have v vector equals dr vector dt, where r vector is the displacement vector of the particle. So remember that in one-dimensional motion, we are either moving in the x direction with unit vector ex. In this case, you have the velocity to be equal to the derivative of x dt in the ex direction, and it follows suit for y and z in the ey and the ez directions. Now let us look at velocity in two-dimensional motion. So consider the two-dimensional coordinate system below. Let us start by drawing our y and our x-axis. Our x-axis has unit vector ex and our y-axis has unit vector ey. This axis meet at a common point O. For a particle or a point P, the distance from the origin to the point P is the displacement vector r vector. This distance is x, while this distance is y. So clearly we see that the displacement vector r vector of the particle is given by r vector equals xex plus yey. So from v equals dr dt, that is the instantaneous velocity, we discover that v vector will be equal to the derivative of xex plus yey dt. It therefore implies that our velocity v equals vxex plus vyey. So now let us look at the velocity in three-dimensional motion. So consider this coordinate system. Clearly we see that the position or the displacement vector r vector equals xex plus yey plus zez. From velocity equals the derivative of the displacement vector to the derivative of time, we therefore have v vector equals the derivative of xex plus yey plus zez dt, which therefore equals to vxex plus vyey plus vzez. Thanks very much for watching GILFORD'S lectures. Please like, share, comment, and discuss this channel with your friends. Please help promote the channel so that we'll be able to reach out a good number of students, we'll be able to reach out a good number of universities, and we'll be able to impact a lot of students with physics and engineering concepts. Thanks again.